And the next talk is going to be given by Madeleine Udell from Stanford University. And she is a professor there. Before that, she was a professor in Cornell. And again, the title of the talk is very interesting, Hunting the Hessian. The floor is all yours.
Great, thank you. And remind me what time I should go until.
45 minutes.
45 minutes, great. Okay. So welcome. I hope you all had a very refreshing lunch because we're about to go Hessian hunting. So I want to convince you that hunting the Hessian is a good idea for AI. I think we're supposed to be doing AI here. And then we're going to talk about how you can hunt the Hessian in high dimensions. Okay, so first let's talk about the optimization landscape of deep learning. I think, if we're going to be doing AI, we can either, as optimizers, I feel like these days we can either do it at the bottom of the stack, where we're working on deep learning optimization, or we can do it at the very top of the stack where we're using the LLM in order to, for example, learn how to use optimization tools better than we could before. So this talk is going to be a bottom of the stack talk. So we're going to have to talk about deep learning landscapes in order to understand why these traditional optimization ideas I'm going to tell you about have anything to do with modern AI. So of course, the best methods for optimization depend on the landscape, right? Do we expect to see local minima? Do we expect to see saddle points? Do we expect to see ill-conditioning, right? What landscape should we expect in modern deep learning, right? So here are some very inspiring figures this is a really old paper at this point from Tom Goldstein's lab, where they showed that without skip connections in the current best architectures of ResNet, the lost landscape looked extremely bumpy, had a lot of local minima. This doesn't look like something that would be easy to optimize, right? Whereas if you add skip connections, right, if you move to the architecture that was then most in favor, this does look smooth. It does look like something that you could optimize with rather traditional optimization methods, right? So more generally, like, what kinds of landscapes do we think we have? This was another really old paper that did some nice theory and experiments in this simple setting of multi-layer perceptrons. What they observed, so remember the index of a critical point is the number of directions of negative curvature. Okay, so if the index is 0, that means you're a local min. The index is greater than 0, it means you are a saddle point. And what they found was that the index of the critical point was related to the error associated with that critical point. So in other words, yes, there were some saddle points that were not so great, but all of the local minima were global. Okay, so in other words, this picture, if you believe this picture generalizes, it tells you maybe you shouldn't be too worried about local minima, but you should be worried about things that are saddles or almost saddles. And this is kind of interesting. If you do more careful numerical analysis, you may find that these are not actually saddles at all. Actually, the negative eigenvalues, you can't tell the difference between -0 or even small positive. So really what this should tell you is that in fact, all of these have this property. The negative eigenvalues are never very large. So it again should give you this picture that's very traditional in optimization of sort of long, flat valleys, but not necessarily even saddles, much less local minima. So let's recall what we know about gradient descent, which is that gradient methods converge very quickly on well-conditioned data. They go right to the minimum, but if you have ill-conditioned data, if you have one eigenvalue of the Hessian much larger than another, then gradient descent will tend to zigzag, okay? We do expect to see ill-conditioning. It's very common in machine learning data. So if I just take a sample of data sets from OpenML and I plot their spectra, so here's the top singular value, the next singular value, the next one, the next one, the next one, the next one. I can see that the largest singular value is much larger than the next one, is much larger than the next one, is much larger than the next one. And then eventually there's a pretty long tail. Okay, so a lot of the energy is in the low singular values, but nevertheless, the large ones are much larger than the rest, often by several orders of magnitude. Okay, yes.
The Hessian here is
Yeah, so this isn't these are data sets, these are not problems. But if you form, for example, a least squares problem or a logistic regression problem, the spectra of the Hessian of those problems is intimately related to these spectra. Okay, and it makes optimization slower. So this is a logistic regression problem that we've solved. Here I'm showing just the spectrum of the original data set. And here I'm showing the convergence of a bunch of really standard stochastic optimization methods that you might try to use to solve logistic regression on such a data set. And they all, if we zoomed in on this plot, it would look like they were all converging. Okay, you would think that they were converging if you didn't have this other method that we've proposed that does some explicit preconditioning that converges to a much lower value of the training loss than all of the others. I mean, these all provably converge. So if you ran it long enough, they should get the same value, but it's sort of long. The difference is large enough that in practice, they don't converge. Okay, so here's an agenda for landscape-aware optimization, which is number one, what should we do about local minima? And I would say that you should ignore them. They're not much of a problem in modern architectures that are sufficiently over-parameterized. With saddles, there's some really interesting ideas for how to approach saddles in a traditional optimization lens. Actually, I love this paper by Royer, O'Neill, and Wright, which notices that if you're solving the Newton system with conjugate gradient, and it turns out that the matrix that you're using is the Hessian is not positive semi-definite, you will either CG will still terminate just fine and give you a solution to the Newton system that you can take, or it will identify a direction of negative curvature, and you can take that. And this is like a beautiful idea that I got really excited, and several of my students tried it in practice on deep learning problems, and it didn't work at all. It seems like saddles just really don't appear in most of the architectures that people use. But what does appear, what does seem to be a real problem is ill conditioning. Okay, and again, it depends on the architecture. Some architectures have it, some architectures don't. But the solution is to precondition. So this talk is going to be about how we precondition in extremely high dimensional problems of the sort that we might expect to see in deep learning. And there, the real challenge computationally is how in the world should we query and use the P by P Hessian matrix, right, of a deep neural net when P is large, right? And the answer is not that we should explicitly form the Hessian ever. So I'm going to give you, I'm going to tell you about a couple of different tools, and I really want the takeaway of this talk to be a collection of useful tools that you might use to get insight into Hessians in your problems, even large problems. And the first tool is automatic differentiation. The second tool is spectral preconditioning, and then a third tool that I'll tell you about at the very end is the online scaled gradient method, which is a very different new tool that we've been developing for Hessian hunting. So first thing I want to remind you all is that ill conditioning is a property of the Hessian. Okay, so we've got a twice differentiable loss. We can write its Taylor expansion as a point in terms of the gradient and the Hessian at that point. And the convergence rate near minimum is going to depend on the condition number of the local Hessian. Okay, so that's the ratio of the top to bottom eigenvalue of that matrix. And this is, I mean, really, it's kind of a funny thing even to write down in a very high dimensional setting. In a very high dimensional setting, you have no way to get access to this, right? Getting access to this requires a full eigen decomposition. It costs P cubed. There's just no way you're going to do it in a large scale setting. Interestingly, you can get access to this, and you can work on the top part of the spectrum. And so the main tools that I'll propose to you will be working on the top part of the spectrum. Okay. This is very exciting. We can access the Hessian, and we can access it efficiently. And the way to do this is through automatic differentiation. Okay, so this is called Perlmutter's trick, and I think it's such a good idea that everyone should know it. Okay, so here's what you do: you compute the gradient using automatic differentiation. Okay, so now I've got a function handle. Once I've done this, I have a function handle for this gradient function. Okay, I can take any vector v I want, and I can define the inner product between G at a point W and my vector V. Okay. And then if I do automatic differentiation on, right, that's a scalar function. So I can do AD on it. And AD on that is the same as the Hessian applied to the vector V. Okay, so I can get my hands on a Hessian vector product just using automatic differentiation twice. Okay. And this is what's going to allow me to understand more about the top part of the spectrum. It's going to allow me to actually plot the entire spectral density of this Hessian. And I will note you could also use this to do Newton CG, but that's not what I'm going to mostly do in this talk, right? Because Newton CG also, you write down the Newton system, and then you solve it using continuity gradient. It only involves Hessian vector products. So you can do it using this primitive. Yes.
Yeah, really stupid question. Does the AD you're using avoid ill conditioning of it? In general, AD would have a condition number, so
Yeah, in general, we have a condition number associated with it. We have not seen problems related to that. I think the way that we're using it is pretty stable. I think if we were trying to get at the smallest eigenvalue, I think we would see problems, but with the largest one, we don't see problems.
that makes sense.
Yeah.
Yeah, okay. But you'll have the answer for me tomorrow.
Tomorrow, yes.
Yeah,
Great. Or my students will, yeah.
okay.
Okay, so let me remind you about how to do Lorentz approximation. So if we didn't care about computation at all, we were willing to do as much computation as we wanted, what would we do to compute a good low-rank approximation to a matrix? Well, we would compute the eigenvalue decomposition. This would take order p cubed flops, okay? And then what we would do is we take the first couple of vectors in U, the first couple of values in lambda, the largest ones, the first couple of vectors in U transpose, and we would form this low-rank approximation to A, just using those vectors, okay? Unfortunately, right, this takes p cubed flops, so I don't recommend you do it in high dimensions. Instead, here's what I do recommend that you do. And here, the picture that I want you to have in mind is that if I have a very large matrix, I can think of that matrix as an operator. That's the right way to think about it. If I take a vector and I apply the matrix to it, what's going to happen to that vector? It's going to end up pointing more along the directions of the largest eigenvalues, right? Eigenvectors, right? In the largest eigen subspace. And it's going to point less in the direction of the smallest ones. So if I take a collection of random vectors, I apply my operator to this, the resulting collection is going to lie not in, but close to the span of the top eigenspace of my operator, okay? And so if I do, for example, QR factorization on what comes out, I will get a basis, an approximate basis for that eigenspace. Okay, so the Nystrom procedure is one, the randomized Nystrom procedure is one nice way of instantiating this idea. So what we do is we draw a random Gaussian matrix, omega. And there are many different choices for this, but this is the simplest one. We compute a random linear sketch. We apply A to the random vectors in omega. We form the Nystrom approximation. What's kind of interesting about this is that once I have the sketch, I've applied A to my collection of S random vectors. I don't need to touch A again. I can get a good approximation to the low rank approximation to A without touching A more than once. This is very useful in a low computation setting where I am, for example, performing this operation via automatic differentiation. Okay. In practice, like don't actually compute the pseudo inverse. There's a better way to do it that you can find in our paper. So the total computation is reasonable. S matrix vector products, right, or S, calls to Hessian vector products, plus order PS squared computation. The total storage is proportional to the dimension of the eigenspace that you have reconstructed. You get a positive definite thing that's always a lower approximation in the lower order to the original matrix. And it only requires matrix vector products with your matrix. So this is a useful tool. How can we use it to do better optimization? Okay. One really simple idea is to use it as a preconditioner. So I'm going to remind you about what a preconditioner does. You have a linear system, AX equals B. This is the same as if I have any positive definite matrix P, I can apply, P or P to the negative 1/2 to the left side of these equations. The solution set is the same. I can then do a change of variables. I could set X equals P to the negative 1/2 C in order to form a system of equations as the same solution set for X. And this matrix is still symmetric, positive definite if A is positive semi-definite, if A is positive semi-definite. But it could have a different condition number, so it could be much faster to solve. So preconditioning works well when the condition number of that preconditioned system is much smaller than the original one. And it's a good idea when it's not too hard to compute p to the negative 1/2. Okay, so let's think about this. Let's imagine we had a best low rank approximation to our matrix. Okay, so that's the one that we would get by truncating the eigenvalue decomposition. The best preconditioner using that, well, what do we want to do, right? If the spectrum looks like this, here's the largest eigenvalue, here's the smallest eigenvalue. What we want to do is we want to flatten the top part of that spectrum, right? This is the part that we know about. This is the part where we have our low rank approximation tells us anything. And what we want to do is to flatten that so everything is at the same level. This is what's going to allow the condition number to be as small as possible, because the condition number is this divided by that. Okay, so here is a matrix that achieves that preconditioning effect. What you do is you have the preconditioner look like this low rank approximation on the top part of the spectrum, and on the rest you have it just be the identity. Okay, so again, it's very easy to write this down if you have a low rank approximation. Okay, okay, you can use this as a preconditioner. Now, if you have an approximate low rank approximation, you can write down an approximate preconditioner that uses that. Okay. The reason why this can be used is that the inverse is efficient to compute. This is just Sherman Morrison word query, but here's a particularly simple form. We're just taking the inverse of a diagonal matrix. And notice, like, I can't take the inverse of a matrix that has zeros in it, so I need to add a little bit of regularization here. So my preconditioner is always going to be a little bit regularized. Oh no, sorry, this is not true. This is the part of the spectrum that I don't know about. As long as lambda is positive, this is. So, yeah. Oh, yeah, sorry. So this is if you wanted to solve a regularized linear system. And that's often useful, even if you're doing something like Newton CG, a little bit of regularization makes it more stable and it tends to work better. Yes.
Said something like fast food.
Mostly because it's simpler. Yeah, there's a wide range of these low rank preconditioners, low rank approximations, and I expect most of them to work pretty similarly. It's mostly a question of how easy it is to form and apply it. Okay, so on linear systems, this can be very effective. So here's an example of random features regression. And what you'll see is that if you just did QR, you can solve it. It's not that large a problem, but it takes about 1,000 seconds to get to, and it returns one answer in machine precision. If you're using conjugate gradient, you would converge down at a linear rate like this. If you try to precondition with a diagonal, which is a really common idea, and in some ways it's an idea that underlies methods like Adam. Then you actually converge down at a slower rate. It doesn't necessarily go fast. But if you form the Nisman preconditioner, it takes a little while to form the preconditioner, right? That's when you're computing the low rank approximation, and then you converge down much faster. And this is a pretty typical picture that my group has been sort of really hammering this tool for a while now in all sorts of different optimization applications, and it really works quite in a quite wide range of applications, very robustly. So this isn't like a cherry picked picture. As long as your matrix, right? I mean, as long as you're working with a squarish matrix. Yeah. So questions here. Okay. So let's move to a deep learning setting. And I want to tell you about a deep learning setting that's it might sound a little bit toy. And I'm going to tell you some reasons why we've been liking this setting. So here, it's called physics-informed neural networks. And the idea is that you're going to use deep learning in order to solve PDEs. How are you going to do that? Well, you're going to look at the system of equations that describes the solution to the PDE. Okay, so here U is the solution to the PDE, Z is a point in your domain omega. And you know that a certain differential operator acting on the solution has to equal some things at certain points in the domain, and it has to equal a different operator has to equal some other things at points on the boundary. So I can write down this picture like this. I know something about what U has to satisfy on the boundary and what it has to satisfy everywhere in the interior. So this is a really dumb idea. Here it is. Let's minimize the residual. We're going to model the U as a neural net, right? Controlled by some weights, omega. The input is going to be a point in the domain. The output is going to be a value of the solution at that point. And we are going to train the weights of this neural net in order to minimize the residual of the equations describing the PD. Okay. Why is this a really dumb idea? Gradient descent, you wouldn't need to take a second derivative to do gradient descent, but just the optimization problem. Let's not talk about algorithms yet. Why is this a bad optimization problem to solve? If you wanted to get a solution to your PDE. Yeah, well, you need many samples for sure, right? Because otherwise there might be some statistical error associated with approximating what should be an integral is a sum, right?
Singularity. You're going to get
We
singularity.
could get singularities. I guess you could blow up, and that might not even be modelable in your neural net architecture. That's a reason. One optimization reason that really annoys me about this is that you've got a bunch of, much more than that the sum of all each is zero. You know that each of them individually should be zero, right? And it might be that some of the equations are much easier to get to zero than others of the equations, right? And what we've done is, essentially there should be a dual variable for each of these, right? That sort of weights how much, each of these points in the space matter. And we should add them up according to the dual variable, but here there's no dual variable in sight. We've just done a straight sum. And so what it means is that, if some are much easier than others, this is related to the idea that it's a very ill-conditioned problem, and it is a very ill-conditioned problem. Okay. So I might find that I have a solution that's very near zero, and it could still have a very bad relative error. Okay.
Why would that line up with coordinates?
Why would that line up with coordinates?
Usually this, you can have this happen all over the place, and it doesn't really matter
Yeah.
unless your values line up with coordinates, and then you know that you've got a bad problem. So I'm a little confused.
Then it's very ill conditioned.
Sum is over
Yeah.
coordinates. Anyway, I'm probably just being stupid.
No, my sum is not over coordinates. It's over collocation points. I've sampled points in the domain. And I'm minimizing the error in the PD residual at each of those points individually. And so the way that I sample the points can also matter for the control over the actual sort of residual error in the solution based on this.
You just really don't want the two norm.
If I'm doing a deep neural net, I want a two norm.
Yeah.
The other thing that's sort of worth remarking on is that most of the real successes of deep learning are with classification problems. And this is a regression problem. Regression problems turn out to be much harder and very different. Okay. Okay, so this is a very ill-conditioned problem. If we had a solution to this with zero error, it would probably be a pretty good solution, modulo our choice of the collocation points. But it's a pretty nasty problem. Now, as someone who wants to do hard optimization, I love nasty problems. Okay, so although it's sort of why might anyone ever want to solve a problem like this? I would say this is a starting point for doing more advanced physics-informed machine learning, like operator learning, that I can't imagine being used in the loop of like a PD constrained design. Okay. And then you might be willing to use something that's noisy and not very good as a solution, as long as it was fast for initial phases of the design, and then follow up with a trusted like finite element code. Yes.
Would like a neural net person say that it's over parameterized, you have plenty of zero loss solutions, so it doesn't matter just.
It's fine. Yeah. Right. So you can think about three sources of error, right? There's model error, there's statistical error, and there's optimization error. Okay. And model error you can basically control by over parameterizing your neural net enough so that a zero loss solution is in the domain. Okay. Statistical error you can control through choosing collocation points, and also that doesn't seem to be an issue. We don't see problems with generalization here. So the reason as an optimizer I like this problem is because the main problems with using this framework come from optimization error and not from the other two sources of error, I think. Okay, so pins, they do suffer from under optimization, okay? After training, in most papers that you'll find in the literature, the gradient norm is still in the order of 10 to the minus 2 or 10 to the minus 3, which, you know, optimizers probably want that to be more like 10 to the minus 8, okay? The typical way to train these is to start by running Atom, which would go along like this. And then at a certain point, switch from Atom to LBFTS. Okay. And this is also, this is very weird in the context of deep learning. Usually these are run as full batch. So the gradient, they actually compute the full gradient and pass it to Atom or to LBFTS. So it is like for LBFTS, that's the classic use, right? Okay, when you get to this point, LBFTS actually stalls. You can't go any further. It does not find a step that satisfies both the Armijo and the Wolf condition. And in BFTS, you cannot take a step if you do not satisfy the Wolf condition because your matrix goes indefinite. You need at least a much more sophisticated implementation of BFTS than is currently standard in PyTorch. So you get stuck here. And if you try to run something like a Newton CG method, you can make substantial progress. Okay. And so one paper in my group that appeared at ICML last year proposed a Nystrom preconditioner for a Newton CG method that was able to further reduce the residual by another 1 or 2 orders of magnitude. Now, it looks really good on this plot because it's the number of iterations. If I plotted it as a function of time, it would look much worse because every iteration is much more expensive. And that's why you certainly don't want to start running this method at the beginning.
Okay. All of these are still full batch?
All of these are full batch. There's nothing stochastic here, which is sick because it's clear the problem is a stochastic optimization problem because I started with an integral over the domain.
So
Yes.
you just told the reason why you don't want to run it from the beginning because
Yes.
each iteration. But if you were running it from the beginning, then would it go there with smaller number of iterations? Just the iterations.
Sometimes yes, sometimes it gets stuck.
So it can get stuck.
It can get stuck. Yeah. Adam, right there. There's a lot of theory that none of which quite connects with the complexity of the way that modern architectures look, but this says that Adam finds regions that are nice.
Mhm.
And we don't fully understand how or why it does that, but it is a good idea to start with that. Questions?
That orange line is first Adam and LBFTS.
The order line is first Adam, then LBFTS.
What happens if you just do LBFTS?
If you just do LBFTS, it gets stuck actually sooner. So it doesn't even get down to this long. Or you get stuck at a point where it can't make a step. Okay.
So if you just run it not on the full batch, what happens?
If you run it in stochastic setting, it goes even crazier. You know, LBFTS really doesn't work in the stochastic setting. There's stochastic versions of LBFTS, but they're not super reliable. Yeah.
And also just to clarify, right, this is the PyTorch implementation.
This is the PyTorch implementation of LBFTS. Yeah. Okay, on the other hand, this is a maybe unsurprising, but it's a good sanity check. Preconditioners can improve conditioning. And this is kind of cool. This is actually, I'm going to show you pictures of the approximate spectral density, both before and after preconditioning using the matrix that's formed by LBFTS. Okay, the LBFTS preconditioning. Okay. So these plots are all formed. I have to give credit to this original paper by Youssef Saad and an implementation called Hessian by Mike Mahoney's lab. This is really cool because it enables you to, in PyTorch, look at the entire spectral density of your operator. So you can't compute an eigendecomposition, it's too large, but you can get a sense, right? There's some large outlying eigenvalues. And then there's sort of a bulk of eigenvalues around 0. And here you'll see sometimes it looks like there might be some negative eigenvalues, but they're small. They're not very negative. And we actually think that this is a hallucination. These aren't, that actually, we're not sure that these eigenvalues are actually negative at all. Okay, the total loss looks quite ill-conditioned for HPD, right? Because you see some eigenvalues that are 10 to the 4th, 10 to the 5th, and many that are close to 0. We can't tell how close they are. Okay, but if we apply the LBFGS preconditioner, we can see that this entire spectrum shifts down dramatically and becomes very compressed. Okay, so indeed, it's doing something very good on these problems. And so you can interpret the reason why it's able to get down to much lower values of loss as being an effective good precondition. Okay, and then you can look at right, as I said, don't trust the loss on these problems. Okay, but we can look at the error compared to a trusted solution to these PDEs. And so we can see that after we run Atom, there's still a large amount of error here. A larger error is more yellow, less error is more blue. When we run Atom, there's still a lot of error. If we run Atom plus LBFGS, there's still a lot of error. You can see that there's structure in the error, right? We should be able to figure this out. And then if you run Atom, LBFGS, and Nystrom, Newton CG, our method, there's still some error left, right? It's much better, but there's still signal there,
What
right?
are the rows?
What are the rows? These are 3 different problems. Top row is convection. The second row is a reaction equation, and the third row is a wave equation. Okay. So this is kind of interesting. There's an interplay between what optimizer you use and what architecture you choose, right? We know the architecture should have an effect on all sorts of properties of your deep learning landscape, and one property it affects is the conditioning. As an experiment, I was getting pretty frustrated with pins. I was saying, right, the whole point of this is we're sort of learning a feature basis and then learning, right, a best representation for our solution in the feature basis, but is it actually learning a good feature set, right? Or is the optimization error actually preventing you from even doing as well as a really basic feature set? So with several students in my lab, we tried to just do a good job of basic feature engineering, construct a very basic feature set for these problems, and see how that compared to the solutions produced by these state-of-the-art methods. Okay, and what we did is we constructed a feature learning architecture, which we called SafeNet, which basically has a layer of Fourier features and then one layer on top of that. Okay, so it's really using the random features idea from Reck and Rahimi so long ago. Here, you can see with the standard MLP architecture, here's the spectrum in blue. There are these large outlying eigenvalues. And if you move to this network with these Fourier features, the spectrum is much tighter. Okay, so once you move to this tighter spectrum, you might not need advanced sophisticated optimizers. And I think this is a lot of what's going on even in much larger and harder parts of deep learning, that we've moved to things like transformer architectures, partially because they're easy to optimize. And they're easy to optimize because of things they do, both to the connectivity of different local mins and also to the spectrum local linear solutions.
Madeleine,
Yeah.
are you optimizing the Fourier layer or just the
We're tuning the Fourier weights as well. Yeah. Tuning the frequencies. Mm-hmm. And you can see that actually, as you converge towards minimizing this loss, the spectrum actually gets more ill-conditioned. Okay, so you get to be a harder and harder problem as you go. Okay, but well-conditioned architectures improve fits. So you can see that if I try to minimize SafeNet, I get down to a lower error on sort of all of the terms in my objective function. If I do this with a 4-layer pin, I don't do as well. Okay, I think I'm going pretty slow, but that's good because that means we're actually learning. I'm going to tell you about the fact that you could use spectral preconditioning for stochastic optimization. And here, all of our work on stochastic optimization is really in the convex setting. So it's useful for problems like logistic regression or like kernel SVM that are in the convex setting. We have not found these to be as effective on deep learning problems. And that's for reasons that I don't fully understand yet, which is kind of interesting. So I'm not going to tell you much about this except apply all the low-rank preconditioner ideas I told you to stochastic optimization algorithms, to existing stochastic optimization algorithms. Once you do this, you get algorithms that can have both variance reduction and acceleration, or they can have variance reduction and only use stochastic gradients, but occasionally have to use a full sample, and you get sort of all the convergence rates that you might possibly want. You can extend all of these to a preconditioned setting and get improvements in convergence rate. You can get convergence rates that don't depend on the condition number, which, as I said, is very important. And they're practical methods. They don't require growing batch sizes either for the gradient or the Hessian computation. Okay. They perform well even without tuning. And I would say, so here, like, just sort of look at this. Don't interpret it too much. But what I want you to see is that the original versions of all these stochastic optimizers are in the dashed line. Our versions are in the solid line. And when we're not tuned, when none of the methods are tuned, our algorithms are all doing quite well. The rest are doing not quite as well. If you tune everything, the performance of our algorithms doesn't change very much, right? It really doesn't need tuning. The performance of these other methods gets much better, but you've just done a grid search. You've had to run the algorithm like 100 times in order to do this grid search. Okay, so being able to design an algorithm without tuning parameters can be really important in practice. But also the algorithms are still really unstable, right? You see these excursions down to much lower test accuracy. Okay, so that's stochastic optimization, but you can do this for anyway, the classic large-scale convex ML problems that you might want. Okay, but let me tell you about a new class of methods for hunting the Hessian that I'm really excited about. And these, so far, we only have results in the convex deterministic case. There's nothing stochastic here. Okay, although I think the idea is they should extend because they, okay. So here's the idea. Suppose I were trying to minimize a smooth, strongly convex problem. I'm going to update it using a preconditioned gradient update. So I'm just going to apply some preconditioner P to a gradient. And actually in this paper, in this line of work, we don't even call it a preconditioner because we're not even going to require P to be positive definite. Okay, it's just some matrix I'm applying to the gradient. Okay, and if I do this, then I can prove that this will converge, and the convergence rate depends on the condition number that's induced by, well, if I were positive definite, the metric right associated with this preconditioner. Okay. Now, can I learn a good preconditioner? By good, I mean one that has a much a better condition number. Can I learn that as I do gradient descent? Right. So you can imagine, an update like this, where you say, I'm going to do a gradient update like this, and then I'm going to do something that updates my preconditioner based on what I've learned at the previous iteration. And the answer is yes, you can do this, and people have been doing this for 25 years. The idea is called the hypergradient method, hypergradient descent. Okay. And it has good performance after tuning, but there wasn't much theory until my students came along, and Wenzi Gao came to me with this idea, and it's a really cool idea. So let me show you. It's actually very simple. I can give you an idea of it on one slide, which is that if you have a better preconditioner, you're going to have a smaller condition number, and you're going to get a better contraction factor, right, in every iteration of this preconditioned gradient method. So I can turn that around, and I can say what I want to do is I want to find a better contraction factor. That is what it means to have a smaller condition number, and that is what it means to have a better preconditioner P. Okay. So I'm going to write down the contraction factor after one iteration. Okay. The function value at my updated point minus the optimal value divided by the function value at the previous point minus the optimal value. This version I'm showing you requires me to know the optimal value. You can get rid of that. That's not essential. Okay, so let's write down the improvement in my objective value after k iterations. That's the product of the contraction at each iteration. That's the product of, or just by definition, this surrogate function L. And I'm going to use arithmetic geometric mean inequality and say that's less than or equal to the kth power of the average of the KLs that I've seen along the trajectory. Okay. Once I've got a sum, I am in business. because I can use online learning. Okay, so I can't, I can't minimize this in advance. I don't know what the XKs are, right? These losses, right, they depend on the XKs that I'm going to see in the future. But at every time, I can evaluate this. I can evaluate this L at the current XK, and I can use this to update my preconditioner. For example, using gradient descent on the loss that I see at the current time. Okay, so I can use standard online gradient descent, or in fact, you do better if you do ADAGRAD, but it's not very different conceptually. And I get a guarantee. I get that the sum of the losses that I experience at the sequence of preconditioners is bounded by the one that I would expect at the best possible matrix P star plus order square root of K, square root of the number of steps. Okay, so I can combine these relations, and this tells me that the improvement in my objective after K iterations is bounded by 1 minus 1 over the optimal condition number, right? The one achieved by the best possible P, minus plus some regret. And the regret goes like 1 over square root K. Okay, so again, right, we only get good bounds asymptotically, right? But when K is large enough, this gets very small. And so it turns out to be a good idea. So it's an online acceleration of gradient descent. And the algorithm is super simple. So again, you can adjust the algorithm slightly with something that looks a little bit like a line search, but it can be quite cheap. In order to prove that you get the best of both worlds, that you never do worse than gradient descent, but asymptotically you converge to the same convergence rate as you would have if you knew the best preconditioner or scaling matrix in advance. This is super cool. And it's actually very easy to implement. It's like a real method because these updates to the preconditioner, they look like this. They look like the gradient at the current iterate, outer product with the gradient at the next iterate, divided by something computable. Okay. Or you can also project this instead of working with a P by P matrix, which is unwieldy in high dimensions, right? You can project this onto diagonal matrices, and then it just looks like the sort of element-wise product of the gradient at this iteration, the gradient at the next iteration. The denominator is the suboptimality. So the suboptimality, I agree, yeah, you don't like it. So there's two answers to that. One is that in many settings, you know that the value should be 0, like in the spin setting, right? The other is that this is not our only surrogate, this L, we call it the ratio surrogate. There's another one called the hypergradient surrogate that uses the gradient norm as the denominator. And so we get rid of the dependence on the optimal value entirely. Yeah.
This kind of looks like a reverse Polyak step size. So
yeah, it's kind of, yeah, it's related to Polyak step size, but I don't think that we fully understand the relation.
You could always flip them. The secant approximation, you could always flip.
Yeah.
So it's a goofy.
Okay.
Bars like in bars like Orwell, you see that. There's like the prime one dual, one gives you the grades.
Oh, I see.
The other one gives you grades of the denominator.
Huh. It's incredible how rich just gradient descent is. Okay, right. And so this is the one that comes out of the hypergradient circuit has the right. Okay, what's amazing is that this is actually a real method. So if you run this against a whole bunch of first order methods for optimization, and we've done this experiments on standard test problems for smooth optimization. What we're finding is that, so our method, the HDM best, you sort of choose variance of the algorithm to be as good as possible. It's this brown line. And you can see it's converging down faster than anything except for the black line and the dark gray line. What is the black line and the dark gray line? They're LBFGS, and they're LBFGS with memory 5 or 10. Okay, so here we're running a method with a diagonal preconditioner. The memory is like P. And we're competing, right? The only ones that are beating us are the ones that are using substantially more memory. Like memory like 5P or 10P. So I think this is very exciting. And so we've gotten very excited about it and sort of the potential for using these kinds of online preconditioners in a whole range of problems. But that's all I have about you. Yes. This is so we're running it here with a diagonal preconditioner. Yeah.
How do you get such a big improvement with the condition?
It's surprising, right? I mean, so the improvement, it depends on there being a good diagonal preconditioner, right? It's competing with the best diagonal preconditioner,
What are these?
right? And you still get regret guarantees relative to the best diagonal preconditioner. Now, is there a good diagonal preconditioner? Well, it depends on your problem.
What are the three problems here? That's I guess.
I don't know them well. I don't know them well. Yeah, so this is part of why I like the universe of preconditioners I've presented to you. I've presented to you low rank preconditioners, right? And I would view ubiquitous as an example of a low rank preconditioner. The Nystrom stuff is also an example of a low rank preconditioner. And here you have examples of, right, you have a learning method for diagonal preconditioners. You can also put them together. You can actually take any two fixed preconditioners and you can use this online learning framework to learn a convex combination between them. Right. And so there's a really simple experiment I've been trying to convince my students is worthwhile, which is you can take a diagonal, low rank preconditioner, and then you can learn a diagonal preconditioner, and you can learn weights between them, and you can see for which problems do you want to be a diagonal preconditioner, for which ones do you want to be a low rank preconditioner, right? Yeah, or is the convex combination actually much better than that? We don't know answers to these questions. Okay, so that's basically the end. Yes.
Let's thank.
Great, thanks.